Okay, let's dive right in. Today, we are going to tackle one of the most common and, let's be honest, most stressful problems in all of software engineering. What do you do with code that you absolutely cannot change? We're going to uncover the really elegant solution that Go itself uses all the time to solve this, the adapter pattern.
Does this sound familiar? I bet it does. This isn't some textbook problem. This is the real world for so many of us. You've got this critical piece of legacy code, and it's woven into everything, maybe dozens of services. And your job? Introduce something new and modern without breaking a single thing. The stakes could not be higher.
So what it really boils down to is this. You've got a fundamental clash. The old way of doing things and the new, better way, well, they don't speak the same language. They have different expectations, different structures, but they have to work together. That's the core problem we need to solve.
And here's what that clash looks like in practice. Our legacy printer, it expects you to give it the message right in the print method. Simple enough. But our modern printer, it's designed differently. It expects to already have the message stored, so its print stored method doesn't take any arguments at all. See? Different method signatures, totally different ways of using them, they're completely incompatible.
This is the million-dollar question, right? A full rewrite is just a recipe for disaster. You're talking about months of work, tons of new bugs. It's a nightmare. But if you do nothing, you're stuck in the past. There's got to be a safer way, a better way to build a bridge between these two worlds.
And here it is. This is our answer. The adapter pattern. The best way to think about it is like a universal translator for your code. It's a special piece that you put right in between the old thing and the new thing, and it lets them communicate perfectly. And the best part, neither one of them has to change at all. It is the elegant, low-risk solution we've been looking for.
Now, this whole idea is built on one of the most important principles in software design, the open/closed principle. What that really means is that our systems should be open to adding new features, but closed for any changes to their stable, existing code. The adapter is how you follow that rule in the real world when things get messy.
And why does this matter so much? Well, the benefits are huge for production systems. First, since you don't touch the old code, there is zero risk of breaking it. Zero. You can also migrate slowly, piece by piece. New services can use the modern interface, while the old ones keep humming along. It makes testing easier, and crucially, it's reversible. If the new thing has a problem, you just unplug the adapter. No massive, scary rollback needed.
All right, enough theory. Let's actually build this thing. We're going to create our adapter right now. And we're going to do it the smart way, using a test-driven development approach. That means we are going to define exactly what our adapter has to do before we even write the code for it.
This process is just fantastic because the test itself becomes our blueprint. We start by writing a test that uses the new modern printer interface. Of course, this test will fail at first. We haven't written the code yet. Our entire job is then to write the adapter that makes that test pass. It's a super clean, goal-oriented way to build software.
And here it is. This is the absolute core of the entire pattern. The secret is that our adapter struct wears two hats. To the rest of the world, it looks and acts exactly like a modern printer. It implements that interface. But on the inside, it's secretly holding on to the old legacy printer. It implements the new, but it contains the old.
And here's what that looks like in Go. It's really simple. We have our PrinterAdapter struct. Inside, it has two fields. The first one, legacy, is where we hold on to the old legacy printer. And the second one, message, is the data it needs to do its job for the new interface. This simple little struct is our entire bridge.
Okay, now for the translation logic. When print_stored is called on our adapter, look what it does first. It checks if the legacy object is nil. And let me be clear, this is absolutely non-negotiable in production code. You always have to handle the case where a dependency might be missing. If it's safe, then it calls the old print method, passing in the message it has stored. That's the translation right there in action. Now, this pattern isn't just some abstract idea you read about in a book. It is baked into the very heart of Go's standard library. Let's look at a couple of truly masterclass examples to see how adapters are used to build the robust, flexible systems we use every day.
First step, let's look at Go's net/http package. The rule is simple. If you want to handle a web request, your type has to satisfy the http.Handler interface. And that interface demands just one method, serve HTTP. It's a very clear, very strict contract.
But then you see code all the time that uses a plain old function to handle a request. So, wait a minute, how is that possible? A function isn't a struct. It doesn't have methods in the normal way. So how in the world can it satisfy that http.Handler interface? The answer
is just pure elegance. Go uses an adapter here, but it's not a struct. It's a type based on the function signature, called HandlerFunc. And this special type is given a serve HTTP method that does one simple thing. It calls the function it's wrapping. It's a function adapting to an interface by calling itself. It's honestly one of the most beautiful patterns in the entire standard library.
Okay, our next example is even more mind-bending. In the io package, we have reader and writer. You can think of these as complete opposites. A reader pulls data in from a source. A writer pushes data out to a destination. They are fundamentally different, almost opposing paradigms.
This just shows the true power of an adapter. It's not just for bridging simple methods. It can bridge entire concepts. The io.Pipe function acts as an adapter factory. It creates a writer and a reader that are magically connected. Anything you write to the pipe writer instantly becomes available to be read from the pipe reader. It translates the whole paradigm of writing into the paradigm of reading. It's incredible.
Okay, we have covered a ton of ground. Let's bring it all home and distill everything down into the core principles, the key takeaways that you absolutely need to remember about the adapter pattern. First, let's talk about when an adapter is the wrong tool for the job, because it's not a silver bullet. If you control both interfaces, don't use an adapter. Just refactor them to be compatible. If you find yourself chaining multiple adapters together, that's usually a red flag that there's a deeper design problem. And remember, an adapter can't fix a fundamentally broken system, it can only translate for it.
So when you boil it all down, the adapter pattern is really three things. It's a seam, a clean separation that lets you safely migrate from old to new. It's the key to making the open-close principle a reality. And honestly, it's a huge interview signal. If someone asks you how to handle incompatible systems, this is the answer that shows you get it.
If you only take away one single thing today, let it be this. The adapter pattern is the translator between two worlds. It lets old code and new code coexist peacefully. It makes safe, incremental migration possible. And that is one of the hardest and most important jobs in all of software engineering.
So, I'll just leave you with this question. As you go back to your own projects, take a look around. Where are those incompatible interfaces? What are those legacy systems that are holding you back? What, in your world, needs a translator?